Welcome back, students. In this video, we're going to introduce ourselves to stereoisomers, specifically cis-trans isomers. Before we hop into cis-trans isomers, let's talk about what stereoisomers are. Stereoisomers are a classification of molecules that they have the same connectivity, but they differ in the spatial arrangement of the atoms. So what that means is the atoms are connected in the same way, right? So they're not constitutional isomers where there were different atoms, there was different connectivity. They have the same connectivity, but the atoms are not pointing the same direction. So for example, if we look at something like the disubstituted cycloalkanes that we just considered, right? If this is a methyl and this is a methyl, and then we consider something where the methyl is pointing this direction here, but this direction over here, these would be stereoisomers, right? They are having the same chemical formula, they have the same connectivity, but the way that the methyls are oriented is different. We're going to spend a bunch more time on stereoisomers and learn about all the classifications, but for right now, we're going to focus on cis-trans stereoisomers. I want to draw two compounds for you here. I want to pretend like we're facing this ring. So the part that I'm bolding in right here, that's where your eyeball is pointing to. So I want you to see that there's a hydrogen pointing up and a methyl pointing down, and a methyl again down and a hydrogen pointing up. Let's draw something similar. Again, I'm going to take this, I'm going to bold that to say our eyeball is looking right there. And let's put the methyl up and the methyl up, and then our hydrogens down. Are these compounds the same, or are these compounds different? That's going to be a question that we ask ourselves continuously over the next set of videos. When I look at these, what I see is if I were to take this first compound and pancake flip it, because remember, these are not in chair conformation, right? You can pancake flip now. You take this ring and you pancake flip it and you place it on top of the second ring and you go, hey, those methyls are pointing the same way when I pancake flip it. These are the same compound. Let's do a little bit of a change. Let's draw our cyclohexane ring again. Again, I'm going to bold this. And we'll draw another one. Bold that to say our eyeball is facing that direction. And I'm going to redraw that first compound. I'm going to put the methyl down here, and I'm going to put a methyl down here, and I'm going to put hydrogen up there. So that means when we're looking at the ring, there's two methyls pointing down, there's two hydrogens pointing up. Now if I change this ever so slightly, let's take this, put a methyl here, put a methyl here, put a hydrogen here. Now if I pancake flip that first one, it does not, I cannot get it to turn into that other compound. It's just not going to happen. So these compounds, these are different from one another. These are stereoisomers. And like we said on the earlier page, they have the same chemical formula. They have the same connectivity. They differ in how their atoms arranged in space. Let's talk about cis and trans in the context of a ring. When we're talking about cycloalkanes, when we utilize the word cis, what that means is the two substituents are on the same face of the ring. Remember how we said wedges were pointing up and dashes were pointing behind the plane of the ring? If the two substituents are both wedge, then this is cis. If your two substituents are both dash, then this is also cis. Trans is when one substituent faces one direction and the other substituent faces the opposite direction. So here's some examples of trans. The cis and trans nomenclature and wording is going to be something that we use very commonly in the context of rings, and then later on we'll expand it. There are a couple of ways to draw cis-trans isomers. One way is a way that we just looked at, where you draw your planar ring and you put in wedge and dash bonds. That's one way to illustrate cis and trans isomers. Another way is to look at that ring head on, right, and bold this in, and say that you have a methyl here and a methyl here, and then hydrogen here and here. So this is a way to communicate cis and trans. And then the final way that you could actually communicate cis and trans would be in a chair conformation. So if we go back to the world of chair conformations, when we talked about ups and downs, you know, here is axial up, here's axial down. This is another way to communicate that we have a trans chair, is because this one is up and this one is down, and that is opposite from one another. If you're in my class, this is my preferred route. I think that students do best illustrating whether or not an isomer is cis and trans if we're in that planar ring and we use wedges and dashes. But I need you to be mentally prepared to see any of these notations because they can be used interchangeably. Let's wrap up. In this video, we looked at cis-trans stereoisomers and talked about what a stereoisomer actually is. And we defined cis-trans isomers and looked at notations for cis-trans isomers. What you want to be able to do is to look at a pair of compounds and decide whether they are cis-trans isomers, as well as look at an individual compound and say whether or not the substituents are cis or trans to one another. As always, thanks for your attention. This is Katoni signing out.